started? So there is a lab 0 due today. So be sure to turn it in. As I had said several times, not going to count towards the final grade but required. Okay. There is also homework 1, which was simply saying you read the collaboration academic honesty policy. Okay, please be sure to turn that in. It was actually due Friday, and some people sent me email over the weekend saying they hadn't seen it. So I've extended that date for that homework to tomorrow. And as I said, if your collaboration policy is not signed, we will not return any subsequent grades for it. Okay, so that was something that I had announced. So all you need to do is go there and submit. When you read the policy, that's all you need to do. Okay, so be sure to turn both of those two things in. There is a real homework, like the previous one, a real homework coming out shortly. Okay, that's going to be due next week. And we are almost ready with the background to start thinking about their first real lab. Okay? I will probably see whether to hand that out next week or maybe this coming discussion section. Okay, so there is some significant amount of work that is going to start up in this course. It's a 4-credit class, so you have to really keep up with the material, keep up with the readings and so on. Okay, remember that there are 3 labs and 3 exams. Okay, so there is pretty much every month of the semester there is going to be a lab / an exam. Okay, so just wanted all of you to be sure to be keeping up with all of the stuff that's happening in the class. All right, so we'll start with the recap, then we'll start talking about process management today. So we've done the introductory material. Okay, I gave you an introduction of operating systems. I gave you a history, overview of history of operating systems. We looked at hardware features. We looked at architectural features that are motivated by making the job of the OS more efficient. We looked at, I talked a little bit about the 4 main components in this course, which is going to be process and thread management, memory management, iOS devices, file system, storage, and distributed systems. Okay? Today, or rather towards the end of last class, I started the first of those pieces, which is process management and thread management. Okay? Just to recap, last time I was talking about system calls, and I quickly introduced from an architectural standpoint the 4 different ways of designing operating system kernels. Okay, so he said you could have monolithic kernels, you could have layered design, microkernels, or 4th one, modular. Okay, it's Monday morning. So just to show you, I forgot to do this last time. I said Mac OS X actually derives its heritage from an microkernel and Mac. So this is actually in the root directory of any OS X or on any Mac. You see that there's a Mac kernel sitting there. Okay? So that's what boots up, and then all the other services boot up. So OS X, like most other systems, is now hybrid. It's not a pure microkernel architecture for performance reasons, but still you see remnants of Mac in there. Okay, so, and Mac, as I said, is this microkernel that was designed as a research project in CMU, and both Windows and Mac OS X actually derived a heritage from this microkernels. Today, we are going to continue the discussion on process management. I already talked about the definition of a process. What we are going to do a little bit is to look at execution states of processes. We'll look at system calls to do process management. We'll look at how processes communicate with one another. Okay, so that's the agenda for today. I will actually take a break and start with the story. Okay, because it's Monday morning, so we have to wake everyone up. So every Monday we are going to have a story that we start the class with. Okay? There's going to be a moral to the story, just not a facetious thing. So today's story is about 3 smart men and a fool. Okay, so the story goes as follows. So there are these 3 smart men that are walking around in the forest, and then they see a pile of bones. Okay? First smart guy says that this looks like the bones of these look like the bones of a tiger, and I'm going to prove it by reassembling it and making it look like a skeleton of a tiger. And he does that. Yeah. The second smart man says that doesn't quite prove that that's a tiger. So what I'm going to do is actually reskin the tiger and make it actually look like a tiger. So then he takes some skin and he puts it on a pile of bones, and then it looks like a tiger. The third smart man says that still doesn't prove anything. What I'm going to do is actually breathe life into this tiger and really prove to all of you that this was a tiger. And then the fool speaks up and says, don't you think that's a bit dangerous to do? And then the three smart guy says, stop talking about things being dangerous, let us do what we want to do. And then the third guy goes and breathes life into the tiger. In the meantime, the fool climbs a tree because he's not sure what's going on. So the tiger comes to life and just eats up the three guys. And only the fool survives. Yeah, so then that's the story. Now the question is, why did I tell you this story? What's the moral of the story? Anyone want to guess? Okay, the moral is beware of people who think they know too much, including professors. All right? So generally speaking, we just have to keep in mind that you keep learning. Your learning never stops. Doesn't matter what stage of your life you are in. Okay? So you can never know too much. All right. So with that, we will continue the lecture. So this is just a recap. I defined what a process is last time. Okay. I said a process is essentially a program in execution. It has state. State basically includes the code for the process, the state of the registers, the state of the stack, heap, and so on. Okay. I pointed to the program counter as being one of the key registers that points to what instruction that the process is currently executing. Okay, so all that is going to lead us to what are called different execution states of processes. Okay, now given that you have any process, okay, it can be in one of these 5 states that are listed here and also shown in this picture. Okay, the states are new, running, ready, waiting, and terminated. Okay, the name should suggest if a process is in that state, what is it actually doing? Okay, whenever you start up a new process, okay, always starts in a new state. In the new state, the process is not yet running, okay, but the OS is actually setting it up for execution. It's loading the program into memory to make it a process. It's setting up all the kernel data structures and so on. Okay, that's in the new state. Okay. Once a process has been loaded, okay, it transitions to a ready state where it is ready for execution. Okay, but it is not yet executing. It's just ready and is waiting for its turn to execute on the CPU. Okay. At some point in time, the kernel is going to actually schedule this process for execution. Okay. And at that point, it transitions into the running state. Okay. At this point, this process is actually executing on the CPU. It's running, okay, as the name suggests. Now, one of two things can happen when it's running. Okay. It executes some instructions and then it hits an instruction that requires it to do I/O. Okay, you may be reading from a file, writing to the screen, or doing something that requires some I/O. Okay? If you actually hit an instruction that while you are executing an instruction that requires you to do I/O, then the process is going to transition to a waiting state. Okay, because it's going to wait for the I/O to complete. Okay, it has to wait for that I/O instruction to complete before it can continue execution. Okay, so it's waiting. It cannot continue execution any further. Okay, so it's in the waiting state. Okay. Or what can happen in the running state is the kernel might say, you ran for a little bit, now it's time for some other process to run. So you have to go back and wait for your turn again. If you actually have that, then you go back to the ready state and wait for your turn to execute some more. Okay. And so if your I/O finishes, again you go back to the ready state and wait for your turn. Okay, so you're going to make transitions from running to ready or running to wait and wait to ready and so on. And this is going to continue until you have finished execution of your entire process, at which point you're going to go to the terminated state. And then the process will finish, OS will deallocate the memory and sort of clear up all its state and so on, and then you're done. Okay? So these are all the states that any process can be in. Okay, typically, most of the time, you will be in one of these three states. The new and the terminated are the beginning and the ending state. But at any given point in time, you are going to be cycling between these three states, okay, depending on whether your CPU intensive process, IO intensive, some mix of the two. Okay, is that clear? Okay, so we are going to do an example. Okay, that's the picture from the previous slide. This is the program. Okay, that's going to execute and become a process. So it's a one-liner. It's just going to print hello world and exit. Okay, so now we have to ask the question, what states are you going to transition through in order to execute this one-line program, okay, as a process. Okay, so now clearly you just have to follow that picture. Okay, so you are going to start in new. Okay, from new you are going to go to ready. Okay, that's when this process is now ready to run. Okay, so what happens next?
It starts running.
Okay, good. That's only one thing to do from ready. It's only one outward transition, right? So you're going to be given a shot at the CPU. The OS scheduler is going to schedule you. You're going to start running. Okay, so you're going to make a transition to the run state. You start executing your process. You execute. There's only one line here to execute. So you execute printf. Okay, IO. Right. So basically, the very first thing you do is you start doing IO. So from running, you go to waiting. Okay. And you essentially, as I mentioned to you previously, that's going to trigger a system call. Yeah, that's IO privilege instruction. The OS is actually going to take over and try to print that hello world string on your screen. While all of that is happening, the process is going to wait. Okay. Then this printf is going to complete. Okay. System call will actually finish. Printf will trigger a system call. Okay, that will finish. Okay, so all that happens is once the IO is done, you're going to go back to ready state. Wait for your turn to run again. Subsequently, you will again be scheduled to go to running state. Okay? And then you execute the next instruction that is done. So the process is going to transition to terminate and finish. Okay, so that's the state sequence. Go from new, ready, running, IO, ready, running, terminate. Okay? Trivial program, you just follow blindly that picture there and what the program does, and you should be able to figure out a sequence of transitions. All the things that the process. Now, clearly, this could be, typically, this is going to be a lot more complicated than a one-liner. So, you are going to actually cycle between these states many, many times before you finish. Okay? Any questions here? Should be fairly straightforward. No questions? Okay, so let me ask a question instead. Okay, so why do you go from, if let's say you are running and you do IO, right? So basically you are going to do IO, you go to wait state. Okay, why not go directly back from the wait state to the running state when the IO finishes? Okay, you were running previously, you started doing IO. Now, why did you have to go back to, yes, something to say?
Because you're getting a return value from the IO to make, and you need to kind of check to make sure it got what you wanted and didn't hit it didn't hit an exception or anything like that before returning to processing.
Okay, but in the ready state, you're not executing it, simply waiting for your turn, right? So all of what you said with checking the return value, seeing if the exception still requires you to run in order to check that, right? Multiple hands, yes, you have something to say.
It can't start running again if there's another process.
Okay, so it cannot start running until there's another process. Other suggestions? Anything else? You have something to add?
So when it stopped running to the IO, there was probably a trap.
Yeah.
So when that happens, something else will probably start using the CPU, so it has to wait until it gets scheduled again.
Okay, so basically all of the more recent suggestions are you basically once the IO finishes, yes, you are actually waiting. There is the CPU, something else may be running on the CPU. In fact, something else will be running on the CPU. So some other, either the kernel may be running or some other process may be running. So you can't just start executing because you have to wait for whatever is running to be switched out before you get a turn again. So you have to go back to the ready queue and wait for the CPU scheduler to let this process run again. Okay, so even though you are actually running, so you could have said I was running, I had to do IO, so now I need to run again immediately. That's not how things work, because if a process starts doing IO to maximize the utilization of all hardware resources, the scheduler or the OS is going to let some other process run. If some other process has taken over, it's actually hogging the CPU at that point in time. So you have to go back to the ready state, wait for your turn again. Okay, so that's the reason you always transition from wait to ready, not go back to running, even though that's where you came from. Okay, so something to keep in mind. Any other questions here? Okay, so I'm going to introduce data structure, OS data structure called the process control block, or the PCB. Okay. This is the data structure that the kernel is going to maintain for every active process in the system. This is how the kernel knows about which processes are currently present in the system in any of those 5 states. Okay, what belongs to the process. So it's the data structure that tells the kernel everything it needs to know about the process. Okay, so here are all the things that a process control block, each entry of the process control block contains. Okay, it has obviously the process state. What state is that process in currently, ready, running, etc. Every process gets a number or an ID, okay, process ID of that process. Okay, you can use program counter, stack pointer. So all the registers are also stored in the process control block. Okay. So remember, I said when you context switch, you suspend execution of the process, you have to save the state of that process. Okay. This is where it is saved. This is where you take the register values and you dump them here. This is where they are stored, so that when you resume execution, you are going to load them from the process control block back to the registers, so the process can simply continue from where it left off. Okay. So all of the register values are stored in the process control block as well. Okay. Memory management information. We haven't done memory management yet, but page tables, base registers, limit registers, all of the information you need to manage memory for that process is also stored in the process control block. Okay, as well as other things like the owner of the process, what files does it have open at this point in time, if it is doing communication, what network sockets does it have, a state queue, we'll talk about them in a moment, any scheduling information as well, okay, priorities of the process and so on. Yes, question in the back.
Is it one PCB per process, or is it one for all processes? Is it sort of reflecting what you have up there?
Yes. So I actually kept the question is it one PCB per process or is it one process? So this is a data structure. Okay. I did not say how you implement this data structure. If you implement this data structure as a linked list, say, there will be one entry per process. Okay. This information is per process. Okay. There is an entry in the PCB for each process. Each entry is going to include all of this information. The PCB can use a variety of different data structures. You can use a queue, you can use a heap, you can use an array. How you implement the PCB? Orthogonal to what is in the PCB. So think of this as one entry per process in the process control block. Okay? Each entry points to a process. Okay? And that entry contains all of this information. Okay, is that clear? Okay. Any other questions on the PCB? Okay, so I was talking about scheduling information. Okay, so you can actually assign scheduling priorities and whatnot to processes to decide how much CPU time they get. Okay, all of that is also stored in the PC. Okay, so it's the most important data structure in the kernel in some sense, because it allows you to track all of the processes, all of the resources allocated to the processes, and so the kernel has to maintain this data structure clearly. So whenever you have a new process, it has to create a new entry, okay, and fill out as much of this information as may be known when the process starts. And when the process terminates, that entry for that process is deallocated. Okay. Now, one way to think about how you manage the various states. Okay, so I talked about these 5 states. Okay, one way to think about how the processes are allocated to every state is to think about having one queue per state. Okay? You can have a ready queue. Okay? All the processes that are in the ready queue, their PCBs are actually placed in that queue. Okay, so I'll show you a picture here. Okay? So think of, so there is a queue for every state. Okay? There's a run state, there's a wait, that's a run queue. There's a wait state, there's a wait queue. There's a ready state, there's a ready queue, and so on. Okay? So what you can think of is for every process that is in that particular state, okay, you basically, its entry is actually in a queue that corresponds to that state. Okay? So the ready queue has a list of all the processes that are ready to run. They're simply waiting for a turn to execute on the CPU. The wait queue has a list of all the processes that are doing I/O. Okay? In fact, there is typically a wait queue for each I/O device. This is not logically a unit one queue. It may be many queues, one for every device. So you may have a disk wait queue or a network wait queue or a graphics card wait queue, whatever the I/O device may be. But for the purposes of the class here relation, there's only one. Okay? For all processes doing I/O. Yeah, so every state, okay, every process state has a queue. Okay, if the process is in that state, it simply goes to that queue. And when the process transitions from one state to another, its entry. Okay, this is the entry for a single process. Okay, this entry is simply moved from, let's say, run to wait or run ready to run and so on. Okay, is that clear? That is one way to implement this data structure and also track what state you are in at any given point in the process. Okay. So think about the run queue for a moment. Okay, that's the queue corresponding to the running state processes that are executed. Okay. How many? What might be the length of that queue typically? How many entries do you think will be in the run queue? Yes.
Between one and how many processors you have?
Okay, so if you have one processor, how many processes can execute at any given time? One. Okay, there's only one process executing at any given time. How long can the run queue be? It can be only one because that's the only process that's executing. Right? If you have k cores, okay, k could be 2 cores, you have 2 core machine, quad core machine. So your run queue will have no more than that many entries. Because that's the maximum number of processes that can be executing at any given time. Okay? So most of these other queues have no bound on the length. They could be as long as the number of processes in the system. The only queue that is actually bounded in length is the run queue. It is bounded by the number of processors or the number of cores here, because you cannot have more than that many processes actually executing. Then you have cores in the system or processors in the system. Okay, that's the only queue that's going to be short. All these other queues are typically going to be long. Okay? Is that clear? Okay, so we talked about the process control block, we talked about process state queues, and now we are going to talk a little bit about context switches. Yeah, I mentioned this already. So let me define what a context switch is. Okay, the context state switch is the operation that the OS kernel performs in order to suspend the execution of the currently running process, okay, and resume execution of some other process that is scheduled to go next. Okay. So essentially it's switching between processes. That's why it's called a context switch. Okay. So you should ask, what are all the things that need to happen during a context switch? Okay. These are all bookkeeping operations that a OS kernel needs to do. Okay. So what you actually need to do is you take the process that is currently executing and you're swapping it out, you're switching. Okay. So you're going to suspend execution of the process. You are going to save all of its state in the process control block. What that means is you take all of its register values, yeah, that's this step. You take all of its register values, the stack pointer, the program counter, and so on. Okay, you actually copy them from the registers into the process control block because you have space to save that state. Okay, you are actually going to copy that state here. And then you decide which process gets to run next. You take its process control block, you had previously saved its state in its entry, and you take that state and you load them into the registers. Okay, and at that point, that new process is actually ready to start executing, and then you let it run. Okay, so context switch involves a few things. You take the currently running process, you suspend its execution, you take its state, you put it into the PCB, you actually run the CPU scheduling policy or the algorithm, which we haven't studied yet. That's going to come in a lecture or two. You take this, run the CPU scheduler. The CPU scheduler says, here is the ready queue. I am going to pick a process I from the ready queue and let it run next. You pick process I, you take its PCB, you take all of its state, load it into the registers, and then it's ready to go. The reason you have to do this, save the state, is if you did not save the state, the next process is going to go and trample over all of the registers. So you will not know where the previous process left off. Every time you resume execution, you want to start from exactly where you left off. So you should restore everything such that it will look exactly the same before that process was suspended. So you'll just start executing from that point on. Okay? So saving the state of the process and loading the state of the next process is what happens during a context switch. Okay? Now, once a new process starts executing, okay, you allow it to run for a certain amount of time that is referred to as a time quantum. Okay? That's the maximum amount of time the processor, not the processor, the kernel will allow the process to run. Okay? And if it hasn't actually done I/O in the meantime, you will actually have another context switch. You will say your time is up, time for the next process to run. Okay? Now, while you're executing, if you actually happen to do I/O somewhere in between, you voluntarily relinquish the CPU. You say, I'm going to do I/O, so then your process cannot run anymore, so you transition it into the wait queue. Okay? So what goes along with the context switch is the notion of the time quantum. That's the time, or is also referred to as a time slice. Okay, in the textbook, you will see these terms, either time quantum or the time slice. That's the time for which a kernel is going to schedule a process to run. Okay. Typical time quantums may be anywhere between 10 to 100 milliseconds on a typical machine. Okay. Linux, for instance, uses a time quantum of 200 milliseconds. Once a process starts running, it gets at most 200 milliseconds before it is evicted due to a context switch. Okay. In between this 200 millisecond time slice, if it does I/O, then it gives up the CPU and some other process gets to run. But if it is CPU bound, there are no I/O instructions that are being executed, and you get the entire time slice. Then at the end of that, the timer goes off, the kernel runs and says your time is up. You do a context switch, some other process runs. So that's how you are going to schedule processes on the CPU. Okay, so you may get anywhere between tens of context switches to hundreds of context switches a second, and that depends on whether the processes are all CPU bound, CPU intensive processes, IO intensive processes, or some mix. A CPU intensive process is the one that typically doesn't do IO, it just keeps executing. An IO intensive process is one that spends most of its time doing IO. And you can have any mix of these. Okay? If you have largely CPU bound or CPU intensive jobs, then you will have fewer context switches because each process will take most of its time slice. If you have highly IO intensive tasks, you will have very little time actually spent executing because you schedule a process, it executes a few instructions and then it starts doing IO because by its very nature it's IO intensive task. So you can basically switch it out and then you will basically run the next process. Okay? So you may get tens to hundreds of context switches a second. You may even get thousands if you have highly IO intensive tasks. Okay, that clear? Any questions on this? Okay, so I want to show you one thing here. I think I showed you this activity monitor process before. Okay, so this is basically a list of all the processes that are executing on this machine. Right? It's instructive to actually, it doesn't show you which one is running at this point in time, okay, but that's not actually shown in this. But you'll see all the other things that I was mentioning. That's the process ID. Okay, so this is the process number, that's the user of the process, this is the percentage of time it has been running, this is the amount of memory allocated to it, real memory, virtual memory, there are other things you can examine for each process. Okay. Each row here is an entry in the process control block because that's the entry for that process. In fact, this program is simply querying the process control block and displaying all of that information. If you run top on Linux or Unix, you see the same information. This is essentially top with a graphical user interface. What top or PS, any of these commands do is they're simply querying the process control block and they're simply printing out all the processes that they see. And it's actually updating it, as you can see. So these are all the processes that run. And depending on the reason you see them swapping is depending on what is executing and so on, you will basically see them slightly changing order. As processes terminate, some of those entries will be deleted. Start a new process, there will be new entry appearing and you'll see them in this display and so on. Okay? It's just instructive to see what's actually happening on a typical machine, because that's basically coming directly from your PCB or the kernel. Okay, so now having looked at what data structures the OS kernel maintains, all the transitions that the processes make and so on, now we are actually going to look at some system calls that you will use for process management. Okay, I think the previous discussion, you probably did a little bit of this already. I'm going to introduce this more formally. Okay. Now, how are processes created and deleted? They actually are, you actually have to use system calls to do this. Okay. So one thing to keep in mind is every process in the system has a parent process. Okay? Your parent process is the process that created it. Okay? So the first thing is a process can be created by some other process. Okay? Processes don't magically appear out of nowhere. Okay? You have each process in your system has been created by some other process in the system. Okay? So every process has a parent, a unique parent. That's the process that created it. Okay? And this process can create some other processes and they will become its child processes. And those child processes will call this process a parent process. Okay? So there is always a hierarchy, a process hierarchy. Every process in your system has a unique parent. Okay? And then processes can create new other processes. Okay? So this is how the system works. Now you can ask, how does a process create another process? Okay, if you could actually write your own program that creates a child process, for instance. So how does all of that work? Okay, this is done through a system call. So if you actually call the fork system call, okay, you will create a child process. You meaning this process that called the system call is going to create a child process. Okay? Fork is the mechanism by which new processes are created in the system. Okay? So, and I'll talk about how fork works in just a moment, but let me pause for a second and ask you some questions. So I said every process has to be created by some other processes. Okay? So let's say you go to your sort of desktop on your machine and you double click on an icon. Okay? That's going to start up that process. Let's say you double clicked on Chrome. Okay? It's going to start the Chrome browser. That's a process. Now which process actually created this process? Okay? Who is the parent process? Okay. Yes.
The kernel.
Okay. Kernel is the parent process. A kernel could, of course, create any processes. Any other guesses, thoughts?
Be like the UI process.
The UI process. Okay, so typically, kernel typically won't create new processes unless they're system processes. Typically, processes are created by users. The user double clicked on the icon. So the process belongs to the user. So in this case, the UI process actually starts up that process. So the parent is the UI process. Okay? If you're sitting in a terminal, okay, and you type a command, let's say you start up extern or some terminal, and you have a shell prompt and you type a command, okay, you create a new process. So you ask which process is the parent process. This one should be easier. Yes.
The shell process.
Okay, the shell process. Okay, so what the shell is doing is accepting input from the user and it is spawning new processes. Okay? So you will actually see, if you look at if you do top and you see the right column, you can actually see the parent process. Okay? In fact, if you have a Linux machine, access to a Linux machine, if you do PS tree, okay, that's the process tree, you will see the hierarchy. Okay, we say what parent process belong, which process created some other processes, and so on. In fact, I'm sure that if you go to that activity monitor, there is a way to see the processes hierarchically. I'm not sure how. View. Okay, so I'm not sure how to actually. So there is a way to see it here. All processes hierarchically. So now you see launch D. Okay, so that's a parent process. If you expand it, you'll see all the processes are started by launch D. Okay, your GUI process actually calls launch D and it starts up all these processes. You double click on a Mac, that's the parent process that actually takes that input and it starts. Similarly, if you see the shell process, so that's my equivalent of a GUI process. Okay, there's one for the kernel, it has its own launch D process. You see that there are some kernel processes that the kernel itself has started. Okay? When the process boots up, there is process 0, that's the kernel. Okay? And that's the very first process that boots up. Okay? So it gets process ID 0. The kernel actually starts its own launch D, and that's the one. So all of these will actually have launch D as its parent process. Okay, so the kernel is sort of at the root of your process hierarchy. That's the thing that has started it all. Okay? So all these processes will have a parent, and each process will have its own parent, and so on. Okay? So that's your process hierarchy in your system. Okay? Now every time you double click, this thing is going to start a fork and is going to create a new process. That's the one that you have created, or you have a shell, you will see the same hierarchy in there. You do PS3, you will see the same thing. Okay? Now let's come back to fork and see what it does. Okay? What is fork going to do? Fork is going to create a new process. Okay? So you should ask, okay, what should the new process do? You create a child. What should that child process be doing? Okay? Now, there are a couple of ways to implement fork. And in this case, in the Unix way to create a child process is to have child processes resemble their parents. When you create a child, the OS doesn't actually know what the child process should do. So what it does is it simply creates a mirror image of the parent process. Okay? In fact, the child process is an exact replica of the parent process. They are exactly the same. Okay? So the way actually fork works is it takes, when a process calls fork, what the OS actually does is it takes a snapshot of the process that called fork, and it takes its entire memory state and it replicates it. Okay? So the parent and the child, when fork is called, are exact mirror images of one another. They are exactly the same. So the user created a child process that looks exactly like the parent process. Okay? So that's how fork works. Now you should say that's not very useful because you are just creating duplicates of yourself. Okay? You want the child process to typically do something else. Right? So I double click on my Chrome browser. Okay? This GUI process calls a fork and it creates a duplicate of itself. That's not very useful because what you want that child process to do is actually start running Chrome. That's what you created that child process for. Okay? So how do you do that? Okay? The way you are actually going to do is you have a second system call called exec. Okay? Exec is short for execute. So what you want the child process to do is to execute something else, start executing something else. Okay? So typically the way you will create a new child process, you call fork, create a child process, and you tell the child process, go execute this program. Okay? So the child process in this case will actually start, you will do an exec on the Chrome program and then it will start executing Chrome. Okay? So typically fork and exec go in pairs. Okay? You create a fork. Typically in the child process, the fork is going to be sort of followed by an exec. And the exec will specify which file to execute. In this case, we'll give the file name for Chrome. And then the child process will actually start executing Chrome. Okay, there are some subtleties here. I'm going to talk about them in just a moment. But I want the basic concept to be clear first. Okay? So what you want to do is you want to let's say there is a process A. Okay, it calls fork. Okay, it creates a child A prime that is going to look exactly like A. Okay, but we want A prime to execute something else. Okay, So it's going to say exec, and then you can give whatever you want to exec, let's say Chrome or Firefox or whatever. Then A is actually going to become Chrome. A prime rather. Okay. This is the same process. Okay. So basically this just becomes it. So you have the process A, that's the parent, and this is the child process. Right. This transforms itself to Chrome. Yeah, how it does that, I'll talk about that in just a minute. Okay, so two key system calls are process management, fork and an exec. Fork creates a new copy of the parent process. Exec causes that any process that calls exec to start executing whatever program you specify in the arguments of exec. Yeah. So now let's talk about how fork and exec actually works. Okay. Here is a C program that is going to show you how fork works. Okay. And I'm going to also give you some insight into how this works. So here is the fork. Okay. This is the main program. All it is doing is it's taking a string from the user and it's calling fork. Okay. This fork is going to create an exact copy of this whole process. Okay. So there are two of them. They do the same thing. Okay. Now what is going to happen in the child, if you see, is the child is actually going to execute this code for exec. Okay. So the child will, after your fork, the child will actually go and execute exec, and the parent is going to do something else. Okay. So the thing to keep in mind is until when fork is called, you have two processes that look like mirror images of one another, but they both start executing, but they execute different things. Okay, the parent executes something else and the child executes something else. This is how the child is actually going to call exec. Now you should ask, how does that work? Okay, so how this works is, although when you call fork, the return value of fork, okay, is going to be different in the parent and the child. Okay? So although fork creates a new process that's a mirror image of itself, fork will return different values depending on whether you are in the parent process or in the child process. Okay? An important but subtle point. In particular, in the child process, fork always returns 0. That's the behavior of fork. In the parent process, okay, fork returns the process ID of the newly created process. Okay. This is probably the only time you have seen a function that returns two different values depending on which process it executes in. Okay, the fork is a function, that's a system call in particular, is going to return a value. Okay? And the way the OS works is it makes fork return 0 in the child process. And it returns the process ID, which is also an integer, in the parent process. And you are going to use the return value, okay, and check the return value and do interesting things. Okay? In particular, if you have to actually ever write a program that involves fork, here is the skeleton you are going to use. Okay? You are going to say I is fork. Okay? And then this is the template you use. You can almost use this blindly. If you say I equal to 0, okay? So this is the child. And else, say, okay? So what you simply do is you say fork, then after fork you always put an if statement, okay? And you check the return value of fork, and you say if the return value is 0, then the code for whatever your child is going to execute you put in the if part, okay? And if the return value is not 0, you are in the parent, so the code for whatever the parent has to execute after the fork call has to be put in the else part. Okay? If you blindly do this, you are going to get correct code. Because after the fork, you want the parent and the child to do different things. In particular, you want the child to typically call an exec or do something else, and you want the parent to do some other stuff. If this was a shell, if you're writing a trivial shell, you are going to say get input, okay? And then in the fork, you create a copy of the shell. The child is going to exec whatever input you provided, and the parent is going to continue. Parent is still the shell, so it's going to go back to your command prompt and accept more input. So this is how the shell would work, for instance. Okay, so you always write after a fork an if and an else, and then you check the return value of fork, and if the return value is 0, put the code for the child here, put the code for the parent here. That's exactly what you see here. You check the return value, this is the code for the child. This is the else part, this is the code for the parent. Okay. In this case, the parent is simply calling a wait, which is saying, I want to wait for my child to finish. Okay, you say wait with an ID. So the parent does nothing but allow the child to continue execution, and when it finishes, then the wait is going to return. So you wait for the child to terminate, and in the if part, you are just calling an exec. Okay, so you are going to basically call an exec on whatever program. Is that clear? Okay, so we are going to run through an example or two here. Okay, so let's say double click some icon. As I talked about Chrome, this is your GUI process. Okay, what does it do? Okay, you do a fork, then you do this. What do you put here?
Execute Chrome.
Okay, so you're going to basically, this is the part where you need to execute Chrome. So I'm going to write pseudo code here. And this is going to be coming as an input from to the GUI process. It's not but that's what you're going to do. And what do you do here? Okay, wait for more inputs. Okay, so go back and get more input. Okay, so that's the GUI process. All it does is waits for an input and then it acts on the input. Every time you double click, this is what you will do, and then you will go back and simply go and wait. Okay, so then I never told you what exec does, right? So exec is going to execute Chrome, that much you know. Okay, how does it do that is something we need to sort of also understand. Okay. So when the fork is called, it's going to create a child process, and as I said, the child process is a full-blown process that's a mirror image of its parent. It's a completely identical to the parent, except that it has its own unique process ID. But in all other ways, it's the same. It has the same code loaded. And then you come here and you do exec Chrome. Okay, what exec does, as far as it's a system call also, is it basically takes this program, okay, and it wipes the current process completely. It scrubs it and it loads that program. Okay, this program is going to override whatever was in this process. Okay, this is the child process. It's not currently executing Chrome. This has this code loaded. But as soon as you call exec Chrome, it's going to go to the program Chrome, okay, on your disk. It's going to load that program. That program is going to go and override this program. Okay, think of it as you just completely wiped the slate clean, and you took this program and you sort of stuck it here. Okay? And you start executing that program from the very beginning. Okay, so the exec simply replaces whatever program or the code segment of the current process, okay, by whatever is specified in the argument. This is how you are actually, that process is going to start executing Chrome. Okay? It's going to call the OS to load Chrome, and the Chrome is where this instructions actually go and override these instructions, and then you start executing it from the beginning. Okay, is that clear? It's something that you need to keep in mind. Okay, so now let's do a simple exercise. And the exercise is going to be as follows. Okay, you want a process A to spawn a child B, okay, and you want B to create a third process C. Okay, A forks B, B has to fork C. Okay, that's the exercise. Now, question is, what is the pseudo code to achieve this process hierarchy? So what's the code for, what's the skeleton for A going to look like?
It's already there.
It's already here. That's the first process. Okay. Okay. So A is going to call fork. Okay. Fork is going to create a child process. So now there's process A and there's process B. B and A look the same. B is also going to look like this. Okay, so now We want B to spawn C. So how do we do that?
Inside the child if statement block, you fork again.
Same thing. Okay. So we want B to create C. Okay. Now, so that says only B should do this. So this is where the code for the child process is going to go. You don't want the parent also to create another child. Okay. So what you will do is in this if part, you are going to write another 4. Okay. Okay. And you are going to recurse. Okay. This thing is going to look exactly like that. So you are going to say if j equal to 0, this is the code for C, and else that's still the code for B. Okay? Clear? So we could have an exercise where we say, okay, create this process hierarchy, A spawns B spawns C, A should sprint hello, and B should sprint something else, and C so then basically this print after you fork should come here, because only A has to execute that, and if B in this case is spawning C, so first you do this, and then if it has to do something, that code goes here, and if C has to do something, that code goes there. Okay, is that clear? Alright. So now let me erase this. And so you can create any process hierarchy you want. You can do this. Okay. Have a parent process that creates 2 child processes. How do you do that? Okay, you have to fork twice. That's right. Will this do it? Let's create called fork twice. Does that do this? Yes.
No, because the first process you fork is going to fork again, so you have fork.
Okay. So if you actually do this, you say, okay, A create 2 children processes, so I'm going to call fork twice. Okay, this is actually going to give you 4 processes, not 3. Okay, the reason is after the first 4, okay, you have created A and B. Okay, and both A and B are mirror images and both are here. Okay. So both will continue execution. So A will go and his next statement is to call 4. So A is going to create C. But B is also executing. B will also go and call 4. So what you will end up if you do that is this. Okay. So if I say have a parent spawn 2 processes, don't call 4 twice. In this manner. You do have to call 4 twice, but not this. Okay. Yes. Or something to say.
If you want the parent only to fork, then you could make sure that I is not equal to null before calling fork.
Yes. So you want I to be not equal to null. Okay, but that's exactly right. So the second fork actually has to go here, not there. Okay, because you don't want a child to execute that fork. You only want A to execute it. So you call the first fork. Okay, and then basically this is you have A and B that do the same thing. Okay, B is going to enter the if, and you do whatever B needs to do. He's going to print some messages or do something. And A and only A needs to call a second fork, so that fork has to go here. Okay, so basically you say J equal to fork, J equal to 0. This is the code for C, else this is still the code for A. If you do this, you'll only get 3 processes. If you do that thing that is called fork successively, you'll get 4 processes. So both the parent and the child will call. Okay, so use of fork is a subtle thing. So you don't want to arbitrarily start creating unnecessary processes. Okay. So one homework exercise or potential things that you can get on tests and so on is some process hierarchy of this sort, saying have a process, create the following hierarchy and have each of these processes do something. Okay. The right way to always do this is to always start with a fork with an if else and say what does the parent need to do, put that here. What does the child need to do, put that there. Then you will never go wrong. Okay, if you just say, okay, I'm going to call fork twice or some such thing and do fork, you will basically land yourself into some trouble. Okay, so this is the way to write correct fork exec code. always. Okay? Is that clear? Okay, so that is fork. Here's a picture. I should have probably shown this to you before. I kept saying fork creates a copy of the process. So this is the parent process. Okay? Here is this exact thing I was showing you. That's where you call fork. This basically creates a mirror image child process that looks, as you can see, they look exactly the same. Okay? Both the parent and the child have a program counter at 4. Okay, the only thing, the reason they now start behaving differently is in this process. In the parent process, the return value of fork is non-zero. Okay? In the child process, the return value is 0. So the way the parent and the child can distinguish themselves is see what return, what was it fork return, and then you can tell yourself, am I the parent or the child? Okay, that is why you need that if, so that the parent can do something else that's different from the child. Typically, you want the parent and child to do different things. Okay? Bless you. Okay, so we talked about fork, we talked about exec. Those are the key system calls. There are a few more, okay, which I will not spend too much time on. Sleep, you need to know what that does. That just causes the process to wait for a certain amount of time. Okay. The other one that is actually as important is a wait system call. Okay. What a wait system call does is it takes as argument any process ID. Okay. And it is going to simply cause the process that calls wait to wait until that process has finished execution. Okay? Is that clear? So wait is simply going to wait for the name process to finish execution. So think of the shell process. Okay? You type a command, okay? And then the shell is actually going to fork a process and exec that command. But it wants to wait for that command to finish before it puts up a shell prompt next. Okay? The way it is going to do that is in the parent, which is the shell process, you fork a new child and then you wait for that child to finish. Okay? So the child may execute in the print. If you do ls or some such thing, it's going to print the directory of the current directory file listing, okay, and so on. And then when that command has finished, wait PID will finish. At that point, the shell knows whatever program or process has started has finished. Let's display the shell prompt again and accept new input. Okay. So this is how trivially a shell process may be. Okay, so there's many other reasons why you need a wait PID, but I just gave you an example of where you may need things like wait. Okay. The only thing to keep in mind is wait PID can specify any arbitrary process. It doesn't have to specify a child process. Okay, you can wait on any process you want. There's no such restriction that says you only have to wait for a child process to. Okay, wait PID takes any arbitrary argument, and if that's a valid process ID, it's going to wait for that process to finish. Typically, you use of wait is you wait for the child process to finish. But that's not a limitation. Wait can take any arguments. Okay, just keep that in mind. Okay. Last call, okay, that we'll talk about is the kill system call that is used for terminating a process. Okay. Just as fork creates a process, kill is a system call that will terminate a process. Okay. So either a process can terminate itself by calling exit, okay, or a process can terminate another process by calling kill. Okay. So when you actually go and terminate hung processes, you are actually sending it a kill signal. You are actually internally calling a kill that is going to terminate the process. Okay. If you go onto a shell prompt, you can call kill and give a process ID. What that is a simple program that just calls a kill system call and gives that process ID and kills that process. Okay. So here is some pseudo code that basically is going to kill a process. So here is fork. Okay, this is the child. So what happens is here the child sleeps for 5 seconds, okay, and then it exits itself. It terminates itself. Okay, in the parent, what you do is you wait for user input. Okay, and if you type that, if you sort of press some user input before that 5 seconds, you are going to go kill the child before it terminates itself. Okay, so this is going to call the kill system call, specify the process ID, and kill the child. So it's some simple pseudo code. You typically don't create processes and kill them for fun. Kill is typically used to terminate processes that you want to terminate for some reason. Okay, from outside. Hung process is good example. Okay. Okay. So for creates process, exec causes the process that calls exec to start executing the named program. Waits for a process to finish. Kill terminates the process. Now again, I should point out that kill, you can specify whatever process ID you want here. You don't have to necessarily only specify child process ID. Okay, you can kill any process you want in the system. Okay. Yes, there's a question there. Sorry, what's that? Can you kill yourself? Yes, you can call kill for yourself. It's similar to calling exit. Okay, so you can kill yourself. You can. Now, what the OS is going to do is whenever you call kill, it's going to see if you have the privilege to terminate that process first. Okay? Only if you have the right privileges will it actually invoke kill. Okay? You can actually go and kill the kernel itself. That's process 0. Okay? But if you're a user process and you do this, it will say you don't have the rights to kill a privileged process. Okay? Typically, you, the user, can kill any other process that belongs to you. This is why there are process owners. Root can kill any process it wants in the system because root is super user. Okay, it has full privileges. You can terminate any processes, including those that belong to other users. Okay, normal users can only kill their own processes. Okay, it doesn't even have to be a child process. You can kill any process so long it belongs to the same user that is executing this process. That's okay. Okay? Root can kill any process because root has full privileges. So this is how kill is going to work. So you'll actually so you have to actually look at the return value because if you specify a process ID that is either non-existent or one for which you don't have the right privileges, this is going to return an error. Yeah, otherwise it will succeed and you will terminate the named process. Okay? Okay, so now you know about all sorts of system calls to do process management. Typically, all of that code is written in C, but you can call system calls from Java. It's a bit clunky, but it can be done as well. Okay, same concepts apply. You can typically call, but you don't usually call system calls from Java. This is typically done in C, but it is possible. Okay? Now let's talk a little bit about processes and sending messages back and forth. Okay, so if you have any two processes in this, any two arbitrary processes in the system, and you look at if there are dependencies between one or another, you'll either call them independent or cooperating. Okay? Independent processes are arbitrary processes that don't talk to one another, don't communicate with one another, or cooperate with one another in any way. Okay? So you may have Word running and your browser running. Typically, your Microsoft Word or Word editor and the browsers don't talk to one another. They just do their own independent thing, independent processes. Okay? But there may be processes that communicate with one another or cooperate with one another to achieve some larger goal. Okay? These processes are referred to as cooperating processes. Okay? So they may work in parallel, they may communicate with one another to do some task and so on. Okay? And if you have these kinds of cooperating processes, you essentially start seeing what you have in distributed systems or parallel systems. In distributed systems, you have cooperating processes, but these are processes on independent machines. They communicate over a network. Okay? Even on a single machine, you can have processes that communicate with one another. Okay? They don't communicate over a network, they simply communicate using the kernel to send messages back and forth. Okay? Typically, server processes have cooperating processes. So if you have the Apache web server, for example, okay, that's simple. So you typically a collection of processes. Okay, if you start Apache or have access to a machine that has Apache running, if you simply do a PS, you will see that there are 20 Apache processes. Okay? They are all cooperating with one another. Okay? The way things work is there's a master Apache process that's simply waiting for network requests. When a request comes in, it hands that request to a child process saying, go process this HTTP request. And that process is going to go take over that request and do whatever the request needs to be done or wants it to do. send back an HTML response or whatever. Okay. So your servers are typically written as a collection of processes. Sometimes they may be written as a collection of threads within the same process, but the same concepts apply. Okay, here the processes are communicating with one another. Okay, so now with that, I'm going to just show you an example of processes that actually communicate with one another. This is going to be the first of our many examples. This is referred to as a producer-consumer process. Okay? Okay, so this is a little bit abstract. So here your producer process that's simply generating some data, okay? And is sticking that data into a shared buffer. Here's a consumer process that's consuming data that's put in the shared buffer. Okay? This Apache example I gave you can be thought of as a producer-consumer problem, where this is the master Apache process. As each request comes in, it simply sticks it into a buffer and hands it to a consumer, a child process, a slave process that's going to take that request and actually process it. Okay? The buffer is the medium for communication between the producer and the consumer process. Okay, so basically you have, here's your buffer. Okay, it could be an array. So this is the producer, this is the consumer. Producer is simply sticking data into the shared buffer. The consumer is taking data from the shared buffer and processing it. This could be request, this could be some arbitrary data. This picture shows you what a producer-consumer does. In subsequent lectures, we'll see how can you write this code such that you have multiple producers, multiple consumers, all sharing a single buffer. Okay? We'll need synchronization before we can implement such code. Okay? At the moment, there's only one producer and one consumer. Okay? No need for synchronization. So here you just have a while loop. You're simply generating some items, it could be request or some other item, putting it into a buffer. Here you are just pulling stuff out of the buffer. Okay? Now, although I showed you this nice looking array, if you write code of this form and have two different processes, this array is not going to work for you because this is a local array. What you want is some data structure that you can share between processes. The way this is typically done is either you send an explicit message from the producer to the consumer, or you have an explicit piece of memory that's shared, referred to as shared memory. Okay. Shared memory is a piece of memory that can actually be shared across RAM of independent processes. Okay. Remember in the very first or second lecture, I said one process cannot access the memory belonging to another process for reasons of protection. If you try to touch some other process's memory, you will be terminated. So if the consumer tries to actually access this buffer and this buffer was in the producer process, it will not be able to. Because for reasons of protection, the OS is not going to let it. Okay? So the only way to actually share this buffer between a producer or consumer is to do something special. Okay? And that special thing is either you have to declare a piece of memory, a shared memory, and say this is a special region that multiple processes can access. That's the only piece of memory that OS will allow processes to share. You can actually share that memory across processes. Typically, RAM belonging to a process cannot be shared with another process. Okay. Or you can send messages. Okay, so producer can send messages. So there are these two ways producers and consumers communicate, in two canonical ways, either message passing or shared memory. Okay. Both require system calls. Okay. Here is essentially producer-consumer using message passing. Okay. So here you produce an item rather than actually using a buffer, you send it as a message. Okay. You say send this item, the OS is actually going to take this message and deliver it to the consumer. So you have a new message. Okay. And in the consumer you have to do a receive, that's actually a system call also, and then you receive that message. Now this is happening on a single machine. The same thing is going to apply when you have producers and consumer running across machines. They're still sending messages. Those messages traverse a network. This message is simply going to the kernel and the kernel is delivering it to a process on the same machine. The kernel is also capable of sending that message off to different machines. But that we'll not talk about at the moment. Here the producer and consumer are on the same machine. So you are doing inter-process communication on the same machine. Can have processes send messages back and forth. Okay, this is one way. And then here is shared memory. Okay, so you actually have to do something special there, which is, I'm not going to go into the details. So that's a call called memory map, mmap. That is how you can allocate shared memory. Okay? Let's not go into the details of how to allocate shared memory, but assume that you have allocated a region, is a special region of memory in which you are going to keep a shared buffer. Okay? So once you allocated that shared buffer, then the code looks the same as what I showed you. Now this is a buffer that's in shared memory, so it's actually shared. So you can treat it as an array. You simply put a data item in that buffer, and the consumer can just simply go and pull data item from that shared array. Okay, as if it was just a simple array in your program. Okay. So this is basically communicating using shared memory. The previous example showed communication, inter-process communication using messages. So these are the abstractions by which you can have processes talk to one another. Either you have to use shared memory or you have to use processes. Okay. You can also use files, not the best way. You can have two processes open the file. For that you don't need anything special. Okay. You can have one process write to a file and another process read from that file. That's also a way by which processes can communicate. You are using I/O, disk I/O to communicate. Okay. You can write output to a file and you can read output. Okay. If you used pipes ever in Unix, that's how you actually things work. You can have named pipes that go to disk and read it, or you can have pipes that go to memory. Okay. But if you want to communicate without having to do any I/O, you have to either do inter-process communication or you have to basically use shared memory. Is that clear? So that's cooperating processes. Okay, so we covered quite a bit of ground. I'm going to end here because we're almost out of time. So just to recap before you go, we talked about process system calls. We talked about fork. We talked about states of execution of processes and cooperating processes. Okay. So we have built enough background, as I said, to eventually start a lab assignment, which we'll be handing out later this week. But this week I'm going to also hand out a homework, okay, that you'll have to turn in. So keep an eye out for that. Okay, so let's end here today.
Stephen, it's on.